Hello everyone, in this video we'll be looking at another example related to dynamics, the Lagrangian function and equations of motion. We'll also be using Python and SymPy to derive those equations. Well, imagine you have a uniform cylinder like here with two unconstrained degrees of freedom. It can rotate about the y-axis, so let's try to demonstrate that. So that's one possibility. It can rotate about the y-axis, like so. But it can also rotate about the z-axis, this vertical axis here. So those 2 degrees of freedom are unconstrained. And technically something like this could be a part of the kinematic chain of a robotic arm. So let's go over to Python and see how we could solve this problem. Okay, so right here I have my imports. So I'm importing SymPy, like basically everything from that library, and then from SymPy physics mechanics I import Lagrange's method, this class here, and the function called dynamic symbols, and also some stuff for just for display purposes. So I also have this helper function to make the output look nicer. Right, so let's run this first cell and the second one as well. First we define symbols and functions. So clearly we need mass. L would be the length of this, or the height, if you will, of this cylinder. Then you have R, which is the radius here. Like if you look from above, you'll see a circle. You have G, which corresponds to the gravitational acceleration, and T, which stands for time. So those are the symbols. And also 2 angles here to denote those variables, those unconstrained degrees of freedom, which are equal in number to the generalized coordinates in this case. Okay, so we define them as theta y, which corresponds to rotation about the y-axis, and theta z, which corresponds to rotation about the z-axis. So I'm using the dynamic symbols function for that. Okay, so let's run this. And now we have to define the position of the center of mass based on the angles. So the center of mass would be halfway the length or the height of this shape, and also like in at the center of this circle if you look from above, like here. So let's run this and display the results in a nicer form. Okay, so this is what it looks like. We have 3 coordinates, so we have to account for that. And now we compute the time derivatives. So we're using the diff method found in the SymPy library. So let's display those results after differentiation with respect to time. So it looks something like this. So now we have the linear components of the velocity here. the velocity of the center of mass. And now it's time to compute the kinetic energy component related to linear motion translation, because basically we can divide or split the total kinetic energy into the translational component or linear component, as well as rotational component related to rotation about its center of mass. Yeah, so that's what we can do. So we have this linear component here, so let's start with this as well. And for this linear component, we use the linear part of the formula for kinetic energy. So it looks more or less like this. I'm using the SymPy function again, just in case, so that the output looks less verbose. And now I'm going to introduce like a column matrix that holds angular velocities. So let's see what it looks like. So we have 0 for x because there's no rotation with respect to the x-axis, but there is rotation about the y-axis as well as the z-axis. So we have those components there as those derivatives here. And then we have the moment of inertia matrix for a uniform cylinder. Let's see what it looks like. So on the main diagonal we have those expressions, and the off-diagonal elements are equal to 0. And basically the cylinder is uniform, so there's no moment of deviation here, so to speak. Okay, as you can see, this is the same as this part here, so which kind of makes sense because it's basically the same type of rotation, whether it's with respect to x here. For example, let's do it just with respect to x. So we have this type of rotation, and as well with respect to the y-axis, it's the same kind of type of rotation. But when we get to the z-axis, it's actually like the moment of inertia of a disk, because if we look from above, it will actually resemble a disk, right? So we could technically rotate it about the z-axis, but you want to really see any difference because it looks the same from above, right? So those are those moments of inertia, and in this case writing it all in matrix form may be a bit of an overkill, but in the case of a more complicated example, this is probably a better way to handle this. So let's compute the rotational component here, and at the same time we're grabbing the first and only element in this matrix. If you remember, normally we would have I times omega squared. Since we're dealing with matrices here, we have to take the transpose of the first matrix here, then multiply it by this moment of inertia matrix, and multiply it by omega without transposing it this time. So this is what we get. And finally we can compute the total kinetic energy and potential energy. Potential energy in this case is pretty easy, so there's not much to cover here. So we have this kinetic energy and the potential energy. And as you hopefully remember from one of my previous videos, that the Lagrangian function is expressed as the difference between the kinetic energy and the potential energy in a system. So let's display the Lagrangian function here, and then we can finally proceed to calculate or to find or form the equations of motion using the Lagrange's method class, and then by calling the form Lagrange's equations method. So let's run this and display the results. So we have two components here. So the one that is related to rotation about the y-axis, and the other one is related to rotation about the z-axis. So let's make it bigger. This is what it looks like after simplification. So I think that's it for now. Yeah, it's pretty easy. And as you can see here, those are not really dependent on each other. So for example, you don't find the second derivative of theta z in the first equation, and likewise you don't find the second derivative, so the acceleration, and second derivative of theta y in the second equation. So they are not coupled, and it kind of makes sense because this rotation about the z-axis seems to be independent of the other rotation. So this is just one example that is still pretty simple, but it kind of shows you a 3D example. So I hope you find this video useful. If you do, please comment, like, subscribe, share, so I can continue making programming videos. Thank you for watching, and bye.